All right. First of all, yeah, let's start by just reviewing or talking about what it means by a tangent line and a secant line. You know what I'm talking about? Usually we think of it in terms of a circle. What do I mean by a tangent line? Tangent line of a circle. Or, and actually, if I say a tangent line, where's a tangent line? Doesn't it come right on the edge? Technically speaking, a tangent line is one that just touches a circle, and it can be applied to a function as well, a parabola or anything else. Tangent line is just going to be one that comes up and touches, so to speak, the line. And technically speaking, how many points am I hitting there on the curve? Actually one, yeah. A tangent line is the line that strikes the curve in one point, or we're talking around it. You know, sometimes on a tangent line, you know, if this curve came on around and went back up, it's going to, of course, hit that again. But it's still a tangent line because it just comes and touches the line. But anyway, that's a tangent line. Now, what's the difference between the tangent and the secant? Well, a secant goes through two points of a circle. It strikes the curve 2 points. Same thing for a secant line to a curve. We're not going to do very many circles here. But, yeah, if you've got a parabola and you're talking about a secant line, then you're going between 2 points like that. Okay? Secant and tangent. Wanted you to be sure they're aware of those two definitions. Okay? Because what we're going to do here is we're going to talk about, more specifically, tangent lines and secant lines of curves of functions. And so that's where we're going to pick up here. And believe it or not, it is going to be tied into limits somehow or another that we started last time. All right. What I've given you there on the handout. See if I can get it to come up now. Did my computer go up too? Who's this one? Still there. Oop. All right, there we go. What I've got there, handout on the handout, is I've got a function, and we're going to be talking about the tangent line of a function. And so one way that we could do this, and in calculus, turns out tangent lines are important little lines, so we're going to spend a little bit of time on them. Here I've got a function, f of x equals x squared plus 2. I've already got it drawn out for you. Let's draw the tangent line here at the point 1, 3. Okay, so my tangent line, here's my point 1, 3. So the tangent line would just hit that graph in that 1 point. Theoretically, anyway, it's going to look like it goes through a bunch of them, but anyway, wouldn't it be something like that? And you can draw your own there and see how yours matches up. That's the tangent line. Okay? Like I said, in calculus, tangent lines are going to be important. What we're going to want to know, though, in calculus is B question. How can we figure out the slope of my tangent line here at this particular point, 1, 3? How can I figure out the slope there? Well, I've got my tangent line drawn in. So can I get the slope of that tangent line? Just need another point. I think on mine that I did earlier, I went to this second point over here at 3, I think it was 3.7. Yeah, it's about on mine, that point's about 3.7. You can look at yours, see if there's another one. Your 2 might have been okay to use, but yeah, just go to another point, and then the slope, use the slope formula, right? Y2 minus Y1, X2 minus X1. Calculate your slope. What do you get? Well, this is 1.3, and this was 3.7 on mine. See what yours is. Yours may be a little bit different. That's fine. So we could do it that way. 7 minus 3 over 3 minus 1 is what I get, which is 2. 2 is what I get there. So the slope of that tangent line by this estimate anyway is 2. Now, what's the problem with that method right there? It's very much hinged on you drawing that tangent line perfectly. Because this line, this curve, does have a specific slope at 1.3. 2 is probably close. But are you 100% sure? Would you stake your life on it being exactly 2? Probably not, okay? Because a lot of it's hinging upon, how close did I draw that tangent line accurately? I mean, I could have very well have drawn it just a little bit steeper, a little bit less steep. This is not a good method. It's not a direct method by any means. This is just kind of an estimate. At best, we could just call that an estimate of the slope. So that is what the next 2 I've got on here. Let's try to come up with a little better way of doing this. Okay. So let me see if I can scroll down here. I could earlier from right here. So on number 2, let's get an estimate for that tangent line by using a secant line. Because here's the thing. I'm still trying to find the tangent slope at 1.3. However, to be more precise, and you'll see the technique here or the process that we go through, what I'm going to do is I'm going to use a secant line. So I'm going to come out here to another actual point on the graph. Because, say, let's go out here to 2. Instead of estimating there, let's just go to 2, and it would be, well, we could figure it out. It looks like it's 2.6, but that's definitely a point there. I've got the function, f of x is off my page, but you've got it there. It's x squared plus 2, right? And so f of 2, the y value would definitely be 6, wouldn't it? So we've got a definite value linked into the function. Yeah, it's 6. All right, so that's 2.6 and 1.3. And also I'm using, let me tell you this. I call this point P, and this second point they'll usually denote with a Q, just for notation there. So it's probably not even as accurate as the first one I did, but you'll see how it works here. So what is the estimate of the tangent line using that secant line? Well, it would be the same thing, difference of the y's over difference of the x's. 6 minus 3 over 2 minus 1, 3 over 1, just 3. And like I said, that one's probably not as accurate even as the first one, but let's take our next step. All right, so the second one was 3. With me on that? Any questions on number 2, how I did that? I just went to, instead of a tangent line estimate, I said let's use a secant line there. Okay, so that estimates the tangent line, but how could I get even better using a secant? How could I get an even better estimate of that tangent line? Number 3. Well, I guess I'll leave that there right now. Well, I could get an even better estimate, couldn't I, by using a point not so far out from there. So in other words, come in here, let's go to believe I went to 1.5, yeah. Let's come on number 3. Let's go to the point at 1.5 instead of going to it. I'm still using 1,3. That's where I'm trying to find the tangent line. But let's come out to this 1.5, x is 1.5 point. Wouldn't that be a better estimate of the tangent line? I believe so. Okay. All right. Well, the only thing is I've got to figure out what the y value is right there, and how could I do that? Well, use the function value. Use the function at 1.5. So I do 1.5 squared plus 2. What does that give you? We got it? Wouldn't that be 4.25, I believe? Okay. So what is this? What is the slope of that secant line there? Well, it would be this point is 1.5 now, 4.25 to go along with the 1,3. So that would be 1.5 minus 4.25, the y's first. 4.25 minus the y value there is 3. Divide that by 1.5 minus 1. And that gets me 1.25 divided by 0.5, I do believe, which is 2.5? No. Yeah, 2.5. Okay. All right. All right, well, going pretty good. We've said this gives us more. Another reason this is better is because we're actually using the function, aren't we? We're actually using the function values to calculate this slope. But how could I get even better? Well, I'll show you in a minute how we can get this value real quick. But let me just give you. Let's do one more. Let's use the second point as with UQ with x equals 1.1. You see what I'm doing? I started here at the second point being at 2, then I went to x is 1.5. Now I go with the x is 1.1. You see what I'm doing? I'm drawing in closer and closer here to x equals 1. That second point is coming in closer and closer. That should maybe remind you a little bit. But anyway, all right, let me just tell you that if I do that, the Q point would wind up being 3.21. And so that would put the slope there, that secant line, well, it would be 3.21, minus 3 divided by 1.1 minus 1. It winds up being 2.1. So it's winding up looking like, isn't it? I started this one. This one was the slope was 3. Then I went to slope was 2.5. Now I've gone to the slope is 2.1. It's looking like the slope of that tangent line is pretty close to 2, isn't it? You with me there? Because these secant lines keep getting closer and closer to 2. It looks like, and I'll show you. We can fine-tune it a little more and just see that. But with me on that. You okay with what I've shown you so far? Okay, so we're just taking a point to find the tangent line. We're just using these secant lines, the slopes of these secant lines, to progressively get closer and closer to the tangent line. Now on the back side, let me get rid of all this. I got this. Like I said, I'll show you a quick way to do these calculations using the calculator. Just a second. Look at the back side, and it's just kind of a mine's in color. Yours is just black and white. But you see here the secant line 1. That was the first one we did with the secants. secant line 2, and then secant line 3. Those are the ones we progressively went through. And sure enough, look at that. This secant line, well, it's not, here's the tangent line, the red one. This secant line is pretty well off of the tangent line. Secant 2 is closer. Secant 3, hey, we're getting pretty close there, aren't we? So 2.1, that was the third one. That one has a slope of 2.1. 2.1 is getting close. And that's what I was saying. These are getting closer and closer to the real slope here. And it looks like it is going to 2, but I'll be a little more satisfied with that thought if we can do a couple more. But anyway, I'll do that in just a second. But do you see here, this is kind of the idea of limit here. We're getting closer and closer and closer to this tangent line slope. Kind of has the idea of limit. By letting x get closer and closer, the x is getting closer and closer to 1. So we're coming into 1, the x value 1. So anyway, definitely a linkage there. All right, but let me show you here. Let's do a couple more. That's what I wanted to do with the projector there. So let me kill it. Go back to the board. All right. Okay. All right. Well, there's a way we can set up a table to help us with these slopes of these secant lines. Okay, so let's look at a table of slope values, and we are going to use the same function. F of x equals x squared plus 2 all right, and to kind of set it up like they do in the book, yeah. All right, so we're going to estimate the slope with these tangent lines again. Secant lines, sorry. Right here. Estimate the tangent with slopes. Slope of the tangent. I'll get it right here. Estimate the slope of the tangent using secant lines with that second point, the Q point, say at 1, 3, using the Q value. Now, in general, the Q, the second point, that second point is going to be, well, it's going to be tied into the function. We're just going to use, an x, comma, and then the y value is going to be whatever the y value is, right? That's what we were doing. We were just picking x's. We got closer and closer to 1. We started with x is 2. Then we went to 1.5. So we're starting that Q out, in general, just be an x value that we choose. But then the y value is this, isn't it? Okay, so that's the second point. Okay, and here's what we're going to do. We're going to use x equals, we already used x is 2, 1.5, 1.1, 1.01, 1.001, because those are the ones that are getting progressively closer to my 1. But here's how we can do that in a table. Let's denote the slope of the secant line as Mpq. All right, so that's just, here's the function. I went at 1, 3. I'm just saying, well, pick a Q value out here, whatever it is. That's P, that's Q. I'm going to get progressively closer in. And so I'm going to use then that slope. So what is the slope of MPQ in general? Well, it's still difference of the y's over difference of the x's. But if I don't substitute anything for x here, let's write that and see what happens there. Well, so I'm going between, here's my y's, so I take the difference of those. X squared plus 2 minus 3. See on that? See where I got that? Just the difference of the y's. Over difference of the x's. What would be the difference of the x's? Okay. Yeah, second x minus, yeah, so x minus 1. Okay? Well, notice that does simplify on top to this. A little bit of a process, but it'll be worth it. Because here's what we're going to do. What I can do now is let's just set up a table where I'm going to input these x values, and then in my table the y value, if you will, is going to be MPQ. And I can do that, like I said, on the graphing calculator. You can put in whatever you want to. Let's just put this MPQ, it's x squared minus 1 over x minus 1. Let's just put that in as y1. And then we can just cycle through the x's like we did. Didn't we do that a little bit last time? All right, that's what we're going to do. Let the calculator do the work for us instead of us having to do all the computation there. All right, so put in y1. Again, be sure to put parentheses there. All right, so parentheses, that'll be x squared minus 1 divided by parentheses x minus 1. And then just go to the table because the graph really shows you nothing much that will be helpful. All right, so I'm going to do each of these values. Like I said, we've already done a couple of these, but it doesn't hurt to check. All right, make sure we did them right. But yeah, once we've got that in there, calculating these slopes of these secant lines, this will be easy. All right, so do 2. 2, yeah, it gives me 3, just like we thought. 1.5, 2.5, that's what we got a while ago. 1.1, 2.1. So far, so good. But now we're into some new ones. 1.01, what do you get there? 2.01. This is nice. And then 1.001, 2.0. And now that we've got it set up, we can get as close as we want to 1. I mean, go out to thousandths, to 10,000ths, millionths, if you wanted to. You can get as close as you want to there to 2. All right. So this is pretty nice. And then the other thing, too, is we could do it, we could go to the other side, do it from the left side as well. We could do like a 0.9 and a 0.99, and we could do all those too. But and they may have you do some on both sides. But that's a nice little process there, okay? All right, so again, to emphasize here, what does it appear that these slopes values are going to? It's going to 2. So my first little estimate was pretty good. I was pretty good on my drawing of my tangent line. But it does appear the slopes are going to 2. But this is much more concrete than was that just drawing it in and trying to guess. But yeah, this is a much more scientific, mathematical process of going about this. But it does appear that the slopes of these are going to 2. So what does that tell me? It tells me that the tangent line seems to be slope of 2 at 1, 3. Now, if I go to a different point on that graph, of course, it'll have a different slope. But I could do that. I could do this very same process. Say I pick this to be point P right here. I could do the very same process, get the secant lines, so forth and so on, and I could figure out what the slope of that one is. So Again, the idea here is kind of a limit. What are these values going to as we get closer and closer to the tangent line with these secant lines? Okay? All right.